We are on our last chapter. This is going to be chapter 10, and we're going to briefly go over distributed loads. Now, a lot of the regular statics books put this section kind of earlier in the material before you actually cover centroids. But the thing is, we kind of need to know centroids to work these problems. So I think it's better to do it after we've already learned centroids. So that's why I kind of have it moved at the very end after we've talked about centroids. Now, what we're going to do here with distributed loads is we're going to look at loads that are distributed along lines. Okay? And we're going to use the concept of centroids to analyze these systems. So that's kind of why we needed to wait until we got to this point. For an example, let's say we've got one of those cell phone towers. Let's say it looks like this. All right, and there's our tower. So let's just call it a transmission tower. Okay, so it's standing there and it's fixed in place. Now the wind, let's say it's a windy day, the wind's going to come along and the wind's going to blow into this tower. All right, so if I were to look at the wind, if it's coming from this direction, may look something like this. All right, and we can kind of put a line there. So this here is going to represent the wind. All right, so notice we've got these lines. They are distributed over the length of this transmission tower. So in this case, we'll put that we have distributed forces caused by wind. And you can have other kinds of forces that are distributed in that manner. This is just the one that we picked here. So let's just put etc. But these are the kinds of problems that we're going to look at when you have a length and then you've got forces distributed along that length. Now to go over our equations and everything, let's look at this case here. So what this is supposed to be, this is a beam, and then we've got bags of sand that are stacked on top of that beam. And notice they're not really stacked evenly. We've got more over here than we do over here. But the load here of the bags is distributed over the beam. So it's not just in one place like what we've been talking about before. It's distributed across that beam. Okay, so now we've got that. And the magnitude of the load depends on your X position on the beam. So let's just put depends on position on X axis. And you can see that just by looking at it. Because if we're under here, we have a lot more force being applied than we do over here. Because over here we have more of the bags. Okay, so depending on where we are on this beam along the x-axis, that's going to determine how much of a load that is felt at that point. Okay, so if we say this is B and this is A, for instance, then the load at B is going to be greater than the load at A. Now what we're going to do is we're going to define a function. So let's draw out another version of this. Let's put our beam. Okay, so here's the beam right here. And now what we're going to do, let's make this X, this Y. We're going to draw forces representing the loads caused by those sandbags. So over here we only have one bag, so we're going to have small load. And then as we increase the number of bags, it's going to go up. And then as the number of bags decreases, the loading will decrease. Something like this. All All right. Now, if you connect all these at the top, like that, then we're going to call this right here W of X. Okay. So basically this W of X is going to basically describe the loading. All right, so you'll see right here it says define the function W so that the downward force exerted on a tiny dx equals W times dx. All right, so that's what we're going to do. Might make more sense to put this over here. Let's put it over here. Okay, so that's how we're going to define this W. It's going to be defined by these downward forces that are exerted on small little dx values. Okay, and that's going to give us W dx. Now our units for this, we're going to have W, and that's going to be force per length. So for example, newtons per meter. The dx, that's just a distance. So that's going to be a unit of length. So for example, meters. And then when we do W times dx, we're going to have force per length times length, which, if we use these over here, gives us newtons, which is a unit of force, which is what we want. All right, so we want to find a unit of force because that's what we're looking for. Now, what we're going to do after we do this, we've defined this W. We need to find the resultant force for all of this. Okay, so you don't want to sit here and have to individually find all these forces because you're not going to be able to do that. So we need to find the resultant force, and we're going to do that using this W here. And the equation that we need for that, we'll say FR equals the integral over the length of the beam or whatever the surface is of W of X dx. So this is going to be our equation that we're going to use. Now, if you look at what we've got here, we've got an integral, we've got this W function times dx. Okay, so if you think about that, if we have some function like that, we're doing the integral of this function. Basically, that's finding this area underneath that curve. All right, so that's kind of what we're doing here. So think about that. And now let's look at another picture so you can see that better. So let's just say our W of X looks like that. And then let's pull out a little rectangular area. So this length right here is going to be dx. And what we're going to do is we're going to have a df. Okay, so this represents the differential of our force along this area right here. This area is dA, which is going to equal W times dx. So basically what that's telling you is that your resultant force is going to be the area beneath the loading curve W of X. Okay, because this curve is dictated by the loading that you have distributed across the beam, for instance. So if that gives you the loading, when you find the area under it, it's going to give you that resulting force because it's just summing up all those different loads into FR. Okay, now DF, this DF right here, if we have a point O at the origin, that DF is going to produce a moment about point O. And that moment will have X times DF. It's going to equal X times W of X dx. So this is just finding our moments. X would be the moment arm. So basically that's going to be like that distance there. And then what that ends up giving you, if you go through and you find all of the moment arms for each of the DFs as you go along here, then just like with the centroid, when we had the beam and we balanced out all of the different masses, if y'all remember, we're going to end up with x bar equals the integral of x times w of x dx. And we're going to put that over the integral of w of x dx. Now we already said dA was w dx. Okay, so that's what that is. It's w because this height here is w. So this is just length times the width. That's exactly what we have here. So that gives us the integral of x tilde dA over the integral dA. X tilde is just the distance over to your area. Okay, so now we've got this equation also. And last thing before the examples, our resultant force, since if you notice it's related to the centroid here, it's going to act at the centroid of the area defined by w of x. So if I draw this same thing here, that same figure, let's just say it looks like that. Here's w of x. I'm going to find the centroid of this area, and then my resultant force is going to act at that area, or that centroid location. All right, so that's how we're going to relate centroids to distributed loads. So let's stop there, and then we'll pick it up in an example, and it kind of makes all of this make a lot more sense. See y'all in a few minutes.